Chapter 1 Regressions Linear Regressions Model. Before the 1970s, numerous regression methods were used, including Poisson regressions, logistic regressions, and probit regressions. Each regression model required a unique estimation algorithm by maximizing the specific likelihood for that model. The component of linear regressions consists first, the response y, the linear predictor mu, which is the expectations value of the y, or equals to x and the beta. Third, the distributions of y should be Gaussian distributions. And the variance denoted by var y. Therefore, the Gaussian distributions through log likelihood can be written as follows. For the normal equations from the linear regression model can be written as x transpose w x beta hat. So the w here is as the weighted in the regressions. And the beta hat can be calculating by x transpose x inverse minus 1. X transpose y. True linear regression models consist hat matrix, leverage, residual. We can calculate the residual from our models as follows. The data give the speed of cars and the distance taken to stop. Note that the data were recorded in the 1920s, which refer to the Ezekiel 1930. Therefore, they have only two variables, only stopping distance and speed of car. First models, stop distance, alpha plus beta speed, and model 2, stop distance, alpha plus beta speed square. To perform the data analysis, open the Albatross Analytics and choose the car stopping data. And you can see there is only two variables, stop distance and speed. Therefore, once we want to make new variables just like previous video, next we want to make the new variables which is the speed 2 can calculate by speed square. Hence, just input speed 2 variables and this expression speed square. Click run and our new variables will be appear like this. Speed 2. So this is the square from the speed. To create linear models, we can write the models in the Albatross like this and select the variables speed as the independent variable. Click run and the model will and we can get our model summary. This is the ANOVA. From the ANOVA, we can measure our model is good enough or not to make the modeling by comparisons with the F value to the F tables or our probability value to the significance alpha, 5%. And the sentence model summary gives us information, number of variables, our F value, probability value, our R square, 70%, and the adjusted R square, 87%. And this is our residual standard error and a Jika criteria. As we know that linear regression is an analysis that assesses whether one or more predictor variables explain the dependence regression variables, and the regression has 5 key assumptions: linear relationships, multivariate normality, no or little multicollinearity, no autocorrelations, and lastly, homoscedasticity. A note about sample size: in linear regressions, the sample size rule of thumb is that the regression analysis requires at least 20 cases or 30 cases per independent variables in the analysis. Linear regressions needs two relationships between the independent and dependent variables to be linear. It is also important to check for the outlier since linear regression is sensitive to outlier effect. The linearity assumptions can be tested with the scatter plot. The following the example of scatter plot. Following is the scatter plot residual versus fitted. And this one's normality probability plot, which is shown that our data follows the normality distributions. And lastly, this illustrates the histogram of students' residual. Remember, in the last slides, we have two models. To make our second model, which is stock distance, speed square, choose the speed square as the independent variables. And we can get the model summary. Because we have two different models, we can compare apple to apple which model is good to make the predictions, model 1 or model 2. So, from these comparisons models, we can choose the model 2 as our best model, which is the R-square is 90%, is good enough than the first model, which is only 80%. And we move to second example. The second example, we can using the ozone data, which measured for 330 days in 1970. All measures are in the area of the Uplands CA east of Los Angeles. Refers to Bremen and Friedman in 1985. So, this data consists the temperature of Sandburg. This data consists of Sandburg air force base temperature, inversions base height, Daggett pressure gradients, Vanderburg 500 millibar height, visibility, humidity, wind speed, day of the year, and lastly upper ozone concentrations. And we can read our models as follows. Ozone equals to beta 0, this is our constanta, plus beta 1 temperature Sandburg, plus beta 2 inversions base height, plus beta 3 Daggett pressure, and plus beta 4 is press height. To create the models using Albatross, click Data Import and browse Ozone original datasets. Hence, will be appear like this. In addition, we can write our models like this. And we choose the response as ozones and select our independent variables, which is temperature Sandburg, inf height, Daggett press, and visibility. And click Run. Our models will be appear like this. So, you can see that only 67% the influence of this variable to the ozones. Based on the model summary, it can say that only 60-70% all of these variables can. From the model summary, based on the R-square value, only 60-70% all of these variables can be explained by ozone. But we can see before we create the models, first we have to justify which parameter can be included in our models. And we can justify by the probability of T. Before we make the predictions from our models, we have to fulfill the coefficients can be included or not in our models. And justify by probability T value, comparison with our alpha. Or we can compare T value within the T table. Check VIF and lastly, check our models is good enough or not to make the predictions by justify model checking plot, scatter plot, residual versus fitted, and for the normality test, normality probability plot.